The climate is always changing, and it is the single most commonly used argument against the anthropogenic global warming theory. However, that statement in and of itself has no bearing on anthropogenic global warming, but it's the inferences, both explicit and implicit, that are drawn from that statement that are used as criticisms of that theory. So this video is going to take a look at this statement and the inferences that are drawn from it and see whether they hold any water. There are two main inferences from that statement. One, the climate has changed before naturally without human intervention, so human activity cannot now be causing global warming. That inference is incorrect because the conclusion is not supported by the initial assertion. Two, we are still here after previous climate changes, so there's nothing to worry about from global warming. That too, the conclusion is not supported by the initial assertion, but it also ignores the fact that the climate might be changing in new ways and our current circumstances are different from those previous climate changes. Let's first of all establish some scientific principles that we're going to use throughout this discussion. The first one is that every effect must have a cause. So if you see something change, there has to be a reason for it. You can't just say this is part of a natural cycle or it's happened before and consider that an adequate explanation. You also have to allow for the fact that there might be more than one cause to produce the effect that you're observing. And then your problem comes down to differentiating between those possible causes. We are then left with the immortal words of Sherlock Holmes. When you have eliminated the impossible, whatever remains, however improbable, must be the truth. But science doesn't stop at those sorts of qualitative statements. Science is primarily quantitative. So you have to ask the final question, which is the magnitude of that cause consistent with the magnitude of the effect that you're seeing? Let's take a look at some previous climates. If we go back over 500 million years, we can see there's been periods of both warm and cold climates on the Earth. We've had 4 glacial periods and 4 warm periods. One thing to note here is over the last 50 million years or so, there's been a steady decline in global temperatures. And we'll get back to that in a minute. If we go back 60 million years, you can see that steady decline more clearly, but even during that time there have been warm and cold periods, and each one of these peaks or valleys has an explanation, and we can generally go back and find out what those circumstances are that change the climate. To the far right of this plot, you can see the last 6 million years there's been a steady decline. And let's take a look at that period in more detail. You need to be warned here that the time axis is not linear across the bottom. On the left here, the timescale is in millions of years, and you can see that steady decline that I mentioned before. In the middle part of the plot, it's in thousands of years. And there you can see the cycle between glacial and interglacial periods that have been the case for the last at least 600,000 years. In the middle of the plot, you can see the black line is the onset of the Holocene, the current warm period. That started about 12,000 years ago and peaked about 7,000 or 8,000 years ago. And since then, there has been a steady decline in temperatures until about 100 years ago. After that, the trend reversed itself, and since then we've had a steady warming period. So this plot was done in about 2012, so I've marked on here where the current temperatures are, and that's that dotted line across there. And you can see at no time in the past have we had experienced temperatures that are warmer than the current period. And humans first appeared about 2.8 million years ago, and so we've not experienced temperatures like this since we evolved. That also applies to most plants and animals that currently exist who have not experienced these same sort of temperatures either. It's going to be instructive to take a look at the transition from the last ice age to the current warm period. This is mainly because we have the best data for this, both in time resolution and data accuracy. In that transition, over a period of 6,000 years, global temperatures rose by about 4 degrees centigrade. The global average temperature here is shown in green. You will note that the rise in temperature over this transition is 10 times slower than what we're currently seeing. Interestingly, the temperatures rose slowly and in lockstep with the carbon dioxide, shown here with blue dots, for the first few thousand years. But after that point, about 80% of the warming occurred following the rise in carbon dioxide, not trailing it, as a lot of people seem to think. Let's take a look at the primary causes of climate change on Earth. One of the best known ones is the change in the Earth's orbit, or the so-called Milankovitch cycles. This is where the distance of the Earth from the Sun changes and the orientation of the Earth with respect to the Sun changes, causing the climate to change. A surprising one is plate tectonics. It turns out that the position of the continents determine where ocean currents flow. As the primary cause of our weather and climate are interactions between the ocean and the atmosphere, that changes the climate. Also, the rise of major mountain ranges like the Himalayas, the Andes, the Rockies and the Sierras cause different flow patterns in the winds, so that also causes changes in our climate. And in fact, that period of cooling over the last 50 to 100 million years corresponds exactly to the formation of those three mountain ranges. Obviously, changes in the composition of the Earth's atmosphere changes the amount of radiation that is trapped by it, thus changing the climate. Volcanic eruptions can change the climate for short periods. Impacts can change the climate as well, just ask the dinosaurs. Changes in Earth's albedo is an important factor. The amount of snow and ice on the planet determines how much of the sun's radiation is reflected back into space before it can heat the planet. More snow and ice, the cooler the planet gets, the less snow and ice, the warmer it gets. And of course, if the source of our energy changes, then there's a fair chance that it will affect our climate as well. We can look at the characteristics of some of these potential causes of climate change and eliminate them because they don't fit what's happening currently. For example, we can eliminate Milankovitch cycles because they are too long. The shortest of those is over 20,000 years and the longest 100,000, and the timescales that we're seeing changes on are much shorter than that. Plate tectonics is also a very slow process, so we can eliminate that one. Volcanic eruptions tend to cool the planet, not warm it, so that can be eliminated as well. Impacts can be eliminated because I think we would have noticed a major asteroid impact in the last 100 years, and there hasn't been one. So that leaves us with three possibilities: changes in the Earth's atmospheric composition, albedo change, and change in the sun's energy output. Let's look at each of these in turn. Let's start with the sun. Overall, there's been a general decrease in solar activity over the last 40 years. You can see this in the total solar irradiance, which is the amount of the sun's energy that reaches the Earth. That same trend can be applied to the sunspot number. So if sunspot number and the total solar radiance are correlated, as would seem to be the case, we can use the sunspot number to go back further in time and see what has been happening through the period of the most extreme global warming, that is the last 65 years. Here are the last 6 solar maxima, and you can see the downward trend is very clear throughout that period. Now if we put on the same plot the average global temperature anomaly, you'll see the trend is the exact reverse of that of the sunspot number. So we can now eliminate the sun's energy output changing as a cause of global warming. Let's next deal with albedo change. This plot shows the reduction of ice cover in the northern hemisphere, a combination of ice on land and oceans and snow cover on land. You can see over the last 40 years we've lost 6 million square kilometers of ice. That will reduce the albedo of the planet quite considerably. Let's quickly calculate how much of a reduction in albedo this will cause. The albedo of snow and ice is about 0.9. That means for every 100 watts of energy that comes in, 90 of them are reflected back into space immediately. Land is about 0.3. So for land, we would have 30 watts of energy reflected back into space. And oceans, the albedo is 0.05, which means that all but 5 watts of the energy will be absorbed by the oceans. If you calculate the reduction in albedo as a result of these changes, factoring in the relative area of sea and land, the albedo reduction is 0.8. So that means of those 100 watts, 80 more watts would be absorbed by the Earth for each square meter of this 6 million square kilometer area. Now you can change that into the amount of energy absorbed by the planet as a result of that. And that turns out to be 2 times 10 to the 22 joules. That's equivalent to the total reserves of energy in natural gas, in oil, and our nuclear power generation combined. If you use albedo as the cause for global warming, you unfortunately get yourself into a circular argument. It goes like this. A loss of snow and ice cover is causing a reduction in the Earth's albedo, which then warms the Earth. Or, a reduction in the Earth's albedo is causing a loss of snow and ice cover, which then warms the Earth. So these two turn out to be A proves B and B proves A, which is not a viable solution to our problem. Remember, from our first principle, any effect must have a cause. So what's causing the Earth to warm? If it's albedo, something must be changing to cause albedo to change. So a much better statement is, A warming of the Earth is causing a loss of some ice, which further warms the planet because of the reduced albedo. So albedo here is actually acting as an amplifier of what other changes are causing. So now we're able to eliminate albedo change as the primary cause of global warming. So that leaves us with just one possibility: changes in the Earth's atmosphere. So now let's take a look at that. The thing is, the atmosphere is always changing. We can go back to the very beginning of our planet and see how very different our atmosphere has been and has changed remarkably over the years. The interesting thing here is the rise of carbon dioxide about 3.5 billion years ago and its subsequent decay, followed by the increase in oxygen. Here is an example of some very small creatures changing the composition of the Earth's atmosphere and consequently its climate. We can go back over 1 million years ago and see, along with the cycles of temperature that we talked about earlier, some of the composition of the atmosphere changes. Lastly, over the last 2,000 years, most of that time our composition of our greenhouse gases in the atmosphere, for example, have been very constant. It's only in the last 200 years that quantity has started to increase, and it's increased dramatically to levels that have not been seen for millions of years. A question that we should be asking ourselves is, why is the Earth so warm? If the Earth had no atmosphere, or had an atmosphere that didn't interact with either incoming or outgoing radiation, it would be 32 degrees cooler than it is now. In fact, we'd be living on an ice planet. In fact, we probably wouldn't be living at all. We can take an example, the Moon, which has no atmosphere. The average surface temperature there is minus 16 degrees centigrade. The Earth's average temperature is plus 16 degrees centigrade. So you can see this effect just by measurement. However, you can actually calculate what the temperature of the Earth should be at this distance from the Sun, and it agrees with these sorts of numbers. So what is it about the atmosphere that makes the difference? The Earth gets most of its energy from the Sun. That energy comes primarily in the visible part of the spectrum, and the gases in our atmosphere are transparent to that. So it allows that energy to come through and heat the surface of the Earth, which in turn radiates that energy away in the infrared part of the spectrum. Now, some of our atmospheric gases are not transparent in the infrared, and they absorb that energy and help keep the Earth warmer, the so-called greenhouse effect. So now let's take a look at the composition of the atmosphere. Our atmosphere is primarily made up of nitrogen, about 78%, oxygen, just under 21%, argon, just under 1%. Then we have a bunch of trace gases, such as carbon dioxide at 400 parts per million, neon at 18 parts per million, helium at 5 parts per million, and methane at 2 parts per million. Then we have other trace gases measured in parts per billion, such as CFCs, various oxides of nitrogen, and ozone. This is the so-called dry atmosphere. We also have water vapor in the atmosphere, and that can vary tremendously from 10 parts per million to 5%, and the amount of water vapor in the air depends solely on the temperature of the air. So let's see which of these gases are so-called greenhouse gases and which have no effect on either the incoming or outgoing radiation. These 5, nitrogen, oxygen, argon, neon, and helium, have no effect on either incoming or outgoing radiation. That leaves these 4 gases, carbon dioxide, methane, the trace gases CFCs, nitrogen oxides, and ozone, plus water vapor, to contribute to our greenhouse effect. Now, water vapor is a special case. It's a so-called secondary greenhouse gas because its concentration in the atmosphere, and thus its effect, is solely dependent on the temperature. So it is dependent on these other 4 greenhouse gases to determine what the composition is. So water vapor acts rather like the albedo, being an amplifier of changes in the other parameters. But we have the problem then that there's a very small concentration of these gases in the atmosphere in terms of percentages. But percentages do not matter. What matters is how far a photon can travel before it hits one of these molecules. The path of a photon in a vacuum, assuming there's no massive gravitational force nearby, is a straight line. The same is true if that volume is filled with gases that are not interacting with the photon, so the photon can still pass straight through that volume. Now, if we add a low density of gas that does interact with the photon, so every now and then one of these photons will hit one of those molecules and be directed in a new direction, sometimes forward, sometimes backwards, sometimes sideways. That distance that it travels before it's likely to hit one of those molecules is called the mean free path. And the shorter the mean free path, the more interactions there are. So now let's put a high density gas in there that does interact with the infrared photons, and you can see it gets bounced around all over the place. This is called a random walk. Now 100 years ago, the mean free path of an IR photon in our atmosphere was about 100 meters. So there was lots of interactions. That's why it kept the Earth warmer than it should be. However, today that mean free path is 70 meters. So there's that many more interactions before that photon can escape. That effectively slows the rate at which energy is radiated away from the Earth and heats the Earth up. Well, now we're going to get quantitative. On the left here we have natural forcing only. The black curve is the actual observations. The red and blue curves are the predictions of various models. And you can see the models predict far less warming than is actually occurring. On the right we have the exact reverse situation, that the anthropogenic forces predicted by the models are far too high. However, if you add the two of them together, you get a very much different picture. Again, the black line here is the observations, the red and blue lines are the models, the grey area are the uncertainties on various runs of the model using different scenarios. And you can see that the models do a pretty good job of reproducing the temperatures that we see. So that says a combination of forcings, both natural and anthropogenic, explain the observations precisely. But the majority of the warming that we're seeing is due to anthropogenic forces, particularly the greenhouse gases. So in summary then, the climate is always changing. That is a true statement, but in no way does it detract from the anthropogenic global warming theory. Currently the climate is changing in an unprecedented way, reaching temperatures that no human has experienced, or plant or animal for that matter, and is rising faster than ever before. The only cause that fits this effect is the increase in greenhouse gases in the atmosphere. So if you see somebody who is using the excuse that the climate has changed before and therefore global warming is not human caused, then you should post a link to this video. You can follow near real-time updates on my Twitter channel, drkstrong, and I would appreciate any comments that you want to leave below. Thanks a lot. Until next time, goodbye.